Okay, I suggest we start and then we will see if anybody will join. So, dear colleagues, honorable participants, I welcome you, and it is a pleasure to greet you at the third webinar of the One World YoungStatS webinar series. The focus today will be on composite-based structural equation modeling, particularly on partial least squares, path modeling, and approaches to access composite models. The webinar will present some of the most interesting and recent theoretical developments and applications from younger scholars active in this area of research, and I think you would be able to learn more also during their presentations. The idea for this webinar arose in discussions with Dr. Florian Schubert, also one of today's presenters, during our few meetings on the workshops of the working group structural equation modeling coordinated by Professor Joost Heinecke with 35 years of tradition. I sincerely and greatly thank Florian for all of his great involvement in the setting of today's composite-based C-SEM webinar. That being said, it has to be mentioned that since our second webinar on Bayesian nonparametrics, Young Stats project and One World YoungStats webinars have also received the support from the Institute of Mathematical Statistics, IMS, to whom we greatly thank and hope to satisfy expectations which were the ground for the support. One World YoungStats webinar series is part of Young Stats project of the Young Statisticians Europe initiative, part of FENStatS Association, supported now by both Bernoulli Society for Mathematical Statistics and Probability, as well as the Institute for Mathematical Statistics, IMS. The webinar takes place on a monthly basis with the aim of presenting the most interesting young scholars in the areas of statistics, probability, and econometrics on international level. Our next webinar in June, Wednesday, June 20th, will take place on the topic of functional data analysis with again 3 excellent young scholars and well-selected discussants. And for the fall of this year, we are before finalization of the organization of a joint webinar with the Young Researchers Committee of the Bernoulli Society, Imacurato, Sandro Gallo, and Zhenhua Lin on concentration inequality in machine learning. We thank also for their great involvement, and a webinar on symbolic data analysis, a special topic on the boundary of data mining and machine learning, and the analysis of complex and object-based data. Our today's speakers will feature Benjamin Liengaard of Aarhus University, Denmark, presenting on measurement invariance testing with latent variable scores using partial least squares path modeling. Nicholas Danks of Trinity College Dublin, Ireland, who will present on the role of prediction in composite modeling. And last but naturally not least, Florian Schubert, University of Twente, Netherlands, who will present joint work with Jörg Hensler on confirmatory composite analysis. The discussant for today's webinar will be Professor Jörg Hensler of, again, University of Twente, the Netherlands, among other, Chair of Product Market Relations at the Faculty of Engineering Technology of the University of Twente and Scheide, the Netherlands, and leading expert on composite-based structural equation modeling. In particular, it's a subtype, partially squares, PLS, path modeling, which is interesting from the theoretical perspective as well as useful in empirical studies focused on the success factor for businesses. Please write your questions in the chat. We will try to ask them during or after the presentations. 3 presentations from the speakers will be followed by about 10 minutes discussion from Professor Hensler and responses from the speakers, after which we will open the podium for audience questions asked in the chat or live. We will try to allow you to unmute yourselves, and I additionally point that this webinar is recorded. Sincere thanks again for your attendance, and I would give now the floor to Benjamin Liengaard. Thanks.
Thank you very much. I'll just start by sharing my screen. So I hope you can see my slides now. Yes?
Yes, we do.
Okay. Thank you. So my name is Benjamin Liengaard. I'm an assistant professor at Aarhus University in Denmark, and I finished my PhD a little less than a year ago. And this is a single authored working paper I will present today, which is also a part of my PhD thesis. So the title of the working paper is Measurement Invariance Testing using Partial Least Squares Path Modeling. So first we need to set the context of this research. And to do that, I think it would be easiest for you to think about questionnaire designs. And what we are interested in often in partial least square structural equation modeling is measuring relation between different constructs. And constructs are unobserved variables, also called latent variables. A construct could be, for example, customer loyalty. We cannot observe customer loyalty. So instead, we use, for example, questionnaires where we ask the respondents on a range of different questions that should measure this specific construct. So a way to depict this is, for example, if you want to measure the construct perceived online shopping risk. That could be the risk that the internet users perceive when they should do shopping. Then we could ask these 4 questions here. For example, customer information stored at online shopping website is not safe. And then the rate on this question, for example, from a scale from 1 to 10. In this case, we have 4 indicators, also called items, to measure this unobserved construct. Normally, we would have several constructs in the model, and we could estimate path coefficients or coefficients between these different constructs. This is not the focus of this paper. The focus of this paper is the relation between the measured indicators and the unobserved latent variable. Using partial least squares structural equation modeling, we will get a set of weights denoted by W hat down here, and we use these weights to construct an approximation to the unobserved construct, which I call Y. And this approximation is made as a weighted sum of the different indicators. Okay, so it's like this. So the question I will try to answer is, do we actually measure the same construct when we sample from different groups? So let's say we have a construct we measure for males, and we have the same construct we also measure for females. Well, maybe we're interested to see if the perceived online shopping risk is the same for males or females. Maybe it could be the case that the means of these latent variables differ between the groups. Before we can make such an assessment, we need to assess if any differences in the latent variables are due to genuine differences in the latent variables, or if they're due to differences in measuring the latent variable. It could, for example, be the case that women understood the questions differently than men, and that way they answered differently on the questions because they perceived them differently. So this research or this working paper tries to answer the question, do we actually measure the construct in the same way between groups? This research here built primarily on measurement invariance literature from what is called Invariance-based method. And there is also some measurement invariance procedure in PLS path modeling already, specifically what is called a micron procedure made by Hensler et al. In 2016. This research here differs by explicitly assuming an underlying what is called reflective population model. And doing that, we can do a little more than what is normally done in PLS when testing for measurement invariance, because the micron procedure, maybe Jörg has some comments on that, assumes what is normally called a composite population model, where in my research I assume a reflective population model, which is also widely used in the literature. So this framework I propose here enable researchers to compare latent variable means between groups. It also enables researchers to compare path coefficients between the constructs between different groups. And this framework can also be used with an arbitrary number of groups. So we're not restricted to only looking at 2 different groups, but we could have a range of different groups. We can also use this testing procedure if we have the same observations and we repeat the sampling of the observations, so we have a longitudinal study. In that case, we'll normally expect some correlated errors. And to mitigate this, I'll use a panel bootstrap method to get correct type 1 errors and relevant power levels also. Lastly, I'll just show you an experimental design using PLS. I've not seen this done before. Maybe Jörg has seen some of this before, but I've not been able to find experimental designs in PLS. And this framework here actually enables researchers to do these experimental designs in PLS. Okay. So let's assume we have a specific construct and we have that construct measured between G different groups. The reflective measurement model can be written like this down here. So we have X, that is an indicator, that is an observed variable, and we have Y, which is the latent variable approximation to the construct. So we have different indicators that measures a specific construct. But these indicators are also measured over the different groups. So we have G, which denotes a specific indicator, and G denotes the different groups. So we both have a G and a K indices on the indicators, but we only have a G indices on the latent variable because we only have one latent variable approximation measuring or underlying each of these indicators. Okay, so what we want to test is specifically, if I just look here at this slide here, so I can see there comes something in the chat. Okay, that was not relevant. So what we want to test, or what I want to test in this research is if the intercepts, the alphas, is the same between groups for a specific indicator. And we'll also like to test if the loadings are the same for different groups for a specific indicator.
Benjamin, just one short interruption. Please take care of the time. You will have about 5 to 8 minutes.
Yes, yes, yes. And here's a graphical illustration of the different types of measurement invariance and why this is important. And I think we will leave this for the discussant if we want to elaborate on why it's important to test for intercept and for the loadings when we need to ensure that we have the same measurement model for the latent variables over the different groups. So there's normally 4 different types of invariance that we need to test. That is configural invariance. That is a test that ensures that we have the same number of indicators and the same indicators measuring the different latent variables. Then we have metric invariance. That test if we have the same loadings relating the latent variables to the indicators. We have scalar invariance, which tests if the intercepts are the same between the groups. Lastly, we also have some that's called indicator variance invariance. but I will not go into depth with this for this presentation. If we can ensure that we have the same intercept between groups, we are able to compare latent variable means between the groups. If we have the same loading between the groups, we can compare path coefficient between groups. Normally, these tests are conducted in the order they stand here, so configural invariance first, then metric invariance, and then scalar invariance, and then we can also test for indicator variance invariance. So I'll not go into depth on how these tests are actually constructed. The idea is that we estimate the PLS path model for all of the groups. Then we get the latent variable scores for each of the group. And then we stack these latent variable scores in a specific way. We also stack all of the indicators in a specific way. And the testing equation then will give us a set of coefficients which measures the difference between a reference group loading and another group's loading. So if these differences are 0, that means that the loadings do not differ between a reference group and another group. So for testing for metric invariance, we will have a null hypothesis where the differences between the group and any of the other group is 0. We should test for scalar invariance. Well, then we do a procedure that is similar, but we need to incorporate some assumptions about a marker indicator to identify the intercepts in the model. I will not go into the specific details about this. But the principle is the same about stacking some auxiliary variables and having a testing equation where the coefficients in the testing equation measures the difference in the intercept between a reference group and any of the other groups. The null hypothesis, again, is that these differences are 0. If the null hypotheses are true, then we have scalar invariance, and we can compare the latent variable means across the groups. I've made a small simulation study to test this method, where I simply look at two groups with 2 latent variables in each group. I'll not go into details with this simulation study. I will just briefly mention that over a different set of settings, we'll find that we have good type 1 error, that is the probability of incorrectly rejecting a true null hypothesis corresponds to a preset significance level. And power levels, here we see that the test also has a decent power when we deviate away from the null hypothesis. And there is some proposed procedures which is mainly taken from the C-SEM literature and then slightly modified to fit into the PLS-SEM framework. And I will not go into details again with these, but just to emphasize that this is a stepwise procedure where you need to conduct some tests before you conduct other tests. Okay. So lastly, I'll just show you a brief empirical example. In this example, or the purpose of this example is to show you what this measurement invariance test allows researchers to do. So here I'll do what I call a Latent and ANCOVA model. So the idea is that we want to see if the internet users will change their perceived online shopping risk if they know the risk of doing shopping online. There could be risk of hacking, for example, or stealing credit card information and so on. So to test if this is the case, that they will change their perceived online shopping risk if they're giving this information, then I sampled around 550 observations. They all answered on the same 4 questions related to perceived online shopping risk. Then I split the sample in 2 randomly, And one group were given information about how likely it is that you, for example, get a data breach after doing online shopping risk, and the societal cost of mitigating these breaches. The other group were given similar negative information, but just about heart disease and cardiovascular disease. So again, what is the probability of, for example, having heart disease, and what is the societal cost of these diseases? So then each group has got different informations. And then lastly, I measure the perceived online shopping risk for both of the groups again. So this is post-intervention for both of the groups. Before I can compare all these latent constructs here to see if there is an actual effect of providing this information, I need to ensure that these constructs actually are measured similar between the groups and also between the occasions, because it's likely that giving the treatment or giving the different information actually change how they perceive the questions. Therefore, I do the metric invariance test, I do the scalar invariance test, and I cannot reject the null hypothesis of either. That implies that I actually have measurement invariance over the groups. I will not go into details with these results here. Okay, lastly, when I've confirmed that I have measurement invariance over the different constructs, now I can compare these constructs. Then I can set up an ACOVA model where I investigate if there is an effect of the treatment that is giving information about data breaches. So I have an intercept here, a dummy, a treatment dummy, and I have the constructs here, perceived online shopping risk, and I have an interaction term, which is the interaction between perceived online shopping risk and the dummy. So estimating this equation here, I can see the treatment dummy is 0.28, highly significant, which is evidence for that there is actually an effect of people knowing the risk of doing online shopping. We also find the direct effects or the relation between post and pre-treatment perceived online shopping risk. Okay, so that was what I have. So for conclusion, so I use this measurement invariance testing framework for reflective construct in the PLS framework. I propose tests for metric, scalar invariance, and invariance uniqueness. This allows researchers to do, for example, experimental designs with PLS. Okay, I think I'll just stop here now, so we are about time with the timeline. Thank you very much.
Excellent. Many thanks. It was a great presentation, also more than on time. There should be time now for clapping, I would say, as usual. But basically also we have 2 questions in the chat to be asked before the next presentation. Firstly, Yusuf Zakaria asks, is there any causal assumption between the latent construct and the observed variables? If no, then what is the underlying assumption between the 2 types of variables? And additionally, Max asks, how do you test the power of the PLS model?
Yes.
Thanks. Maybe
Okay.
if you just answer shortly.
Yes, yeah, I'll just answer shortly. So normally, with respect to the first question about causal assumption between the latent construct and the observed variable. So in the reflective measurement model, you normally assume that a change in the latent variable affects the indicator or the observed variable causally. The assumption is that you have an expected value of the error term to be 0, and the covariance between the latent variable and the error term is also assumed to be 0. Okay.
And about the power, the Max question.
Yes. Okay. So
how do you test the power?
Yes. So the way I test the power is example, let us assume, oh, I don't show my slide here. So what I basically do is assume we have one group and we have another group. Then we fix the loading in one group, and then we change the loading in the other group. Then we have, then we should reject the null hypothesis. Then I count the number of times in the total number of Monte Carlo simulations where we reject the null hypothesis of measurement invariance.
Okay,
Uh,
thanks.
Okay.
I think this should clear. I will give the floor now also to Nicholas. Please, Nicholas Danks. Thank you again for the presentation.
Thanks, Andre. Let me just get my presentation shared. Okay. So first, of course, I'd like to thank Florian and Jörg for inviting me to this, and thank you, Andre, for hosting me. So my name is Nicholas Danks, and I've got the honor of presenting some ideas and some opinions I have on the role of prediction in composite modeling. Now, I've tried to base this presentation not on a specific research paper, but just on the general direction and the value of prediction when it comes to composite modeling. So the first details I just want to discuss quick are, who am I? Where can you find me? So I'm on ResearchGate, I'm on GitHub, I've got a personal website, so you're welcome to find me there. My email address is on the screen. But in particular, I want to draw your attention to our structural equation modeling package for the R statistical environment called C-SEM in R. We've now released a version 2.10, and it offers both C-SEM and composite modeling, and it's got a whole lot of awesome visualization options. So if you haven't checked it out, check it out. And if you've got an older version, please update. So I'm going to start off with a bigger picture discussion about why is prediction necessary in research. Eminent methodologists and statisticians are advising now that we move away from categorical validations and binary tests of significant versus non-significant. And they're encouraging us to move towards describing more nuanced uncertainty in our models and the data sets that we test them on. Prediction is particularly well suited to this because it offers us another view of the uncertainty associated with the model. And that is how well our model performs on further samples that it hasn't yet seen. There are also calls within the information systems and general management community to temper our explanatory studies with predictive approaches, particularly when it comes to generalizability and overfit, which we'll look at a little bit later. And of course, more narrowly in the composite modeling field, we've seen now some advice from eminent methodologists to move away from a singular focus on model fit, but rather to complement evaluations of model fits with evaluations of predictive power to support our conclusions on generalizability. So in the general research conversation, we can see that prediction is increasingly important. So let's zoom in a little bit and discuss why should we be interested in prediction in composite modeling. Well, traditionally, we have these two ways of approaching analysis of our models, an explanatory approach or a predictive approach. So what we're seeing now is advice to move towards a joint EP approach. So that is to say that where inferential methods typically take a sample of data and they test a statistical model in order to draw inferences about a population. That would be explanatory modeling. What we seek to add is predictive modeling, where we take a model as estimated, just as I just described, and then we apply it to new cases that it hasn't seen, and we generate predictions from those cases to evaluate the accuracy of our model on unseen data. Now this EP lens provides us several roles for prediction in our explanatory modeling. Firstly, assessing relevance. Now this speaks to the specific practical relevance that practitioners might take from research. It's one thing to report perhaps a structural path with the associated sign and a significance and size. That's seldom of use to a practitioner who wants to know how well will this model be applied in practice for me. And predictive errors and predictive accuracy gives further evidence about the actual utility for practitioners. Further than that, assessing predictability provides additional benchmarks for us to talk about our models and to speak about how those models generalize. And these metrics also allow us to compare competing theories and thus enriching our ability to conduct theory development. So I've discussed some motivations about why prediction is important in general and why perhaps for Composite-SEM it's also important. So let's look now at the particular the way that overfit and generalizability can manifest in our models. So you'll see on the scatter plot on the screen, I've kind of visualized some data points on the XY axis. And I've got a bunch of in-sample data visualized there. So one can think of this as the sample collected at the time of hypothesis testing or model testing. A researcher then investigating this relationship between X and Y might be tempted to fit a linear model as depicted by the green. Now, such a linear model does actually a rather good job of explaining the variance of the data. However, maybe driven by desire to maximize model fit and show better explanatory power, the researcher might be tempted to fit another model, perhaps a nonlinear model, such as the blue line. And one can see the nonlinear model, the blue line, does even a better job of explaining that variance in the data. Now, if we were just evaluating a model from explanatory approach or in terms of model fits, one might wash their hands and walk away and say, look, we have a great model that explains the data very well. But when we introduce further observations, some out of sample data that model hasn't yet seen, we can see that our models actually might generate far greater errors than we'd immediately assumed. So we can see now that while that blue model is really well explaining the variance in the in-sample data, it's now generating a rather large predictive error on those new cases. Whereas that slightly less well-fitting linear model has got much better accuracy on those new cases. So this really is a toy example, but I hope that it can kind of visualize the fact that when we don't consider these out of sample implications, that we're tempted to move into areas of overfit. So now, zooming even closer into specific details of composite modeling, we've seen some recent cautions in the literature that perhaps PLS path models might be particularly susceptible to overfit. So then let's look into a PLS or a composite model and let's see what about the model is it exactly that might be leading to this overfit. So first of all, as I previously mentioned, a focus on model fit criteria, as that previous slide showed, might encourage researchers towards overfit. A slightly more serious issue is in composite modeling, the composites themselves are aggregates. As Benjamin explained, they're weighted sums, which aggregate the indicator data. So to visualize this, I've got this, once again, a bit of a toy example, but I hope it's fairly intuitive. So what I've done is I've represented the signal, the variance associated with the signal that we wish to measure by our various indicators as light blue. And so I've said, look, there's some associated error variance in our indicators, and that error variance, I've shown it as a striped light gray. Now, what the composite-based modeling techniques do is they aggregate not only the signal, but the error variance into our composites, such that our composites become measurement error prone. Now, if the measurement error is systematic across our data sets, such as if it's related to a particular instrument or the application of the instrument, the composite-based technique would tend to overfit those structural path coefficients shown as beta 1. And that is to say that some portion of that path would be related to the signal and some to the error. And what we'd do is we'd see that the model would become overly fit to the error that's idiosyncratic to that data. So this is partially what the authors were alluding to when they said that PLS models are particularly susceptible to overfitting. But there are further worrying considerations. First is that composite modeling techniques are often chosen because of their almost supernatural ability to converge. So we see increasingly complex composite models, and often these models are estimated on smaller sample sizes. Often these two reasons are given for using composite modeling techniques. So these will play a role in overfits, as I hope to show you a bit later. But also there's the common practice of maximizing model fits, or the validity criteria of a model, such as reliability and discriminant validity. We often see indicators being dropped or relationships being fixed in order to maximize our model fits. And this too might be contributing to the overfit problem. So we see on several dimensions there are threats to our composite models becoming overfits. So what I'd like to do then is get my hands a bit dirty and try to visualize and generate for you a intuitive display of how this overfit might take place. So I've taken an incredibly simple composite model. In the top left corner, you'll see it has 2 antecedent, 1 outcome construct, 2 structural paths, and a couple of indicators, 4 indicators per construct. So note that it contains no moderation, no mediation, no higher order constructs, none of the the features that people often use in structural equation modeling that form these complex models. This is a really simple model. So I took the simple model and I said, what would it take for me to overfit it? To demonstrate this, what I did was I simulated a data set, a population composite data set. Now I fixed the parameters so that I've known construct scores, I have known population mean squared error. So now I'm going to talk a bit about mean squared error and what you can think of it as, especially in this context where the construct scores are standardized. Mean squared error can be seen as the variance unexplained, where R squared is often described as the variance explained. So mean squared error is the variance of the error, the predictive error. Now we can generate an in-sample mean squared error, and this would approximate a fit metric or an explanatory power metric. We can also estimate an out-of-sample MSE, which would be at a prediction accuracy or a predictive power metric. And so what I've done is I've taken 1,000 samples from this population. So I've randomly resampled each time from this population simulated data I have. And I've generated an in-sample fit MSE and an out-of-sample predictive MSE for each of those 1,000 samples. Now, with MSE, a lower value is indicative of higher accuracy. So lower is better when you're talking with MSE. So on the right, I've attempted to visualize my results. For each sample size, I've indicated the mean in-sample MSE across the 1,000 samples. And then I've visualized the mean out-of-sample MSE. And what you can see, and so I've shown the known population MSE in a dashed line. And we can see that at smaller sample sizes, even this incredibly simple model is showing dramatic signs of overfit. That is to say, the green line is very low, indicating very good model fit compared to the known mean squared error. And the out of sample error is very high or very bad compared to the known MSE. And we can see that this trend, while it reduces as sample size increases, it continues for rather large sample sizes. So what I hope to show you with this visualization is that even for an incredibly simple model and relatively sizable samples, there's a dramatic overfit that we're seeing in the composite-based PLS estimation method. So hopefully this serves to give you some idea that even beyond other considerations, that there is some inherent overfits in a PLS model. Okay, so I think time is drawing a bit close. So I just want to throw out some takeaways from my discussion. You know, why would we conduct prediction on our models? Well, first of all, it gives us a case level versus a model level analysis. The model level analysis is very important. There's nothing to be taken away from that. But it's a value for us also to analyze the case level, to look at things like residuals, predictive error. Are there cases that are outliers in terms of predictive error? How do these cases relate to the data? We can generate evidence to support the generalizability of the model. Does the model generalize across contexts? Did the researcher consider drawing a separate sample from a similar context at a different time? And how does the model compare across those contexts? What is the practical utility of our model? Will it be useful for practitioners to apply this model in practice? Or is this simply an academic model of academic research? And finally, we can then conduct model comparisons, not only in terms of the standard model fit criteria, but also in terms of their predictability. And I think that should be all for me today. So.
Okay, thanks a lot. Again, clap, clap, like one would say. And we also have two short questions, maybe to answer before we continue. Firstly, Laura Trinchera asks, in the simulation, the prediction accuracy is calculated on eta 1 or on the Y's. And then Bunga Pratiri also asks, how do you calculate population MSE in one of the slides earlier? Maybe if we start with Laura's question.
Okay, so Laura, in the simulation, I'm focusing on the outcome construct as the focal construct for the predictive accuracy. So we're calculating it on the outcome construct. And then how do I calculate the population MSE? Well, when I simulate the data, I play God. And what I do is I create the data by hand. And so that is, I take the equation that represents the signal in the data, and I take random normal data and I actually induce that signal in the data. And afterwards I add some random normal error to that data so that it more closely approximates real life data. And because I'm adding the error, I know the mean squared error of that error. I've actually set it as a function of my having generated the data.
Thanks. We will proceed now. Again, congratulations for excellent presentation. We will proceed with Florian. Florian Schubert, please continue.
Yes, one second, I will briefly share my screen.
We just shortly add all of the questions. Other questions in the chat will try to be asked later when we end with the presentations. So please just continue asking in the chat. Thanks, please.
So you should see my screen now, right? Perfect.
Yes.
Yeah, then thanks, Andre, for providing me the opportunity to present one development that was developed together with Jörg Henseler and Theo Dijkstra, and which is called confirmatory composite analysis. Before I start with my presentation, I will I want to create some awareness that also recently CCAs, or confirmatory composite analysis, was equated or the measurement evaluation steps of partially square pass modeling were called confirmatory composite analysis. And yeah, these measurement evaluation steps differ from the approach that I present today. So yeah, be aware of that. And for those of you who are interested in their differences, I refer to one of my recent publications in the Review of Managerial Science. So yeah, what is confirmatory composite analysis? So confirmatory composite analysis is as the name suggests, a confirmatory approach. And indeed, it's an approach to structural equation modeling, which consists of the following 4 steps. So first, we need to specify a model. Second, we need to ensure that the model is identified. And then we can estimate the model parameters. And finally, we can assess the model. So in the following, I will elaborate on each step. So I start naturally with the model specification. So in structural equation modeling, usually a model is specified with regard to a theory, and the theory comprises concepts. So here highlighted by these triangulars. And then yeah, the researcher postulates some relationships between the concepts and the observed variables. So classically, classically, structural equation modeling is concerned with theoretical concepts, or I call them in the following theoretical concepts, which are assumed to be measured by a set of observed variables. Then to mimic this process in a statistical way, we use the common factor model, which is also called reflective measurement model. So in the reflective measurement model, the concept is represented by a latent variable, and the dominant statistical approach to assess this type of model is confirmatory factor analysis. And examples of such concepts are attitudes or traits. So this is all known and well developed, I would say. On the other hand, also the literature also often talks about concepts that are formed or forged out of other variables. And if we look at such concepts, the reflective measurement model does not seem to do a good job to represent this type of theory. So therefore, we came up with proposing the composite model, which assumes that the observed variables make up an emergent variable. So an emergent variable, here highlighted by C, is a composite that conveys all the information between the variables forming the composite and the other variables in the model. Examples of such concepts are socioeconomic status or marketing, or also fear was mentioned once, because fear is composed by some other variables. And to assess this type of model, we developed confirmatory composite analysis in analogy to confirmatory factor analysis. So here I show you a small example of a composite model. So we have the emergent variable eta, which is composed by x1, x2. Usually in the composite model, these two the ingredients forming the emergent variables are allowed to freely correlate. So here highlighted by sigma 1, 2. And then we have two other variables, y and set, which are related to the emergent variable, so they are allowed to correlate freely among each other. So they are allowed to correlate freely. Then in the literature, it was often argued that the composite model is not a real statistical model in the sense of SEM. I agree if we regard the composite as a single entity, or so if we only consider dash part. But if we embed the composite model in a model that contains other variables, then I argue that it's indeed a model in the sense of SEM. So having a look at the variance-covariance matrix implied by this minimal composite model. So here we see the model implied variance-covariance matrix, and on the main diagonal we have as common the variances. So they are not constrained. Then, do you actually see my cursor? Do you know that? Okay, so then...
We do, I think, yes.
Okay, perfect. Then we have here the correlation, the covariance between y and z, which is also not constrained. But now we see that the covariances between x1, x2, and y, and the same for the covariances between x1 and x2 and z, they are constrained. Namely, we impose here rank 1 constraints, similar as the latent variable model does in structural equation modeling. And don't be confused, because here we have these lambdas, and in this model here, lambdas are not present, right? So the lambdas are the covariance between the observed variable, x1, and eta. So this is lambda 1. Similar, lambda 2 is the covariance between eta and x2. So I express the model in terms of covariances, but in fact the lambdas are dependent on the weights. So it's just to preserve clarity. So here, as you have seen, we have these rank 1 constraints. So I would argue that also the composite model is a model in the sense of SEM. And as you will see later, this also allows us to assess the fit of the model. Then we come to model identification. So what does model identification mean in the context of structural equation modeling? It means that we can uniquely retrieve the model parameters from the population variance covariance matrix of the observed variables. So you can think about it. We have here on the left-hand side the model implied variance covariance matrix of y, x1, x2, and z. And then we have the population variance covariance matrix of these variables. And what we do is we equate all the elements and investigate whether we find a unique solution for our parameters. So keep in mind again, it's actually, we are not interested really in the lambdas, but in the weights. But as I said, the weights are dependent on the lambdas are dependent on the weights. So as you can imagine, it's quite cumbersome, in particular if you have larger models, to check whether we can solve these equations uniquely. So therefore, fortunately, we have some rules of thumb or some rules that we can follow to assess whether our model is identified. And in the context of CCA, where we allow the emergent variable to be correlated with other variables, model identification is rather straightforward. So first thing that we need to ensure is that the scale of the emergent variables is fixed. So we can either do that by fixing one weight, or what we can also do is by scaling the weights in such a way that the variance of the emergent variable is equal to 1. So this is usually the approach taken in the context of partially scarce path modeling. And second, a second necessary condition for identification is that no emergent variable is isolated. So if we have only the emergent variable without context, so if we only focus on this part here in the dash box, then the model is not identified. So we need to have some other variables in the model to ensure identification. And then, yeah, ignoring some trivial regularity assumptions, our model is identified, so we can uniquely retrieve the model parameters. So once we ensured that the model is identified, we want to estimate the model parameters. And yeah, to do so, several methods can be used. So for example, we can use approaches to generalize canonical correlation analysis, such as maxVar or minVar. Or we can also use the iterative partially squares algorithm, which builds the core of partially square structured equation modeling. Or we can also use more recent approaches like generalized structured component analysis, so GISCA. And we can even use the maximum likelihood estimator known from structured equation modeling. So we just need to specify our model a little bit differently. But yeah, together with Jörg, we found a specification that can be used to also specify composite models in such a way that they can be estimated by ML. And if we want, or if we have some knowledge or expectation about the weights, we can of course also use fixed weights. So for example, if we have, we can use weights given by experts, or we can weight the observed variables equally. Then in the last step, we come to the assessment of the model. So the assessment of the model typically involves two parts. So the first part refers to the overall model fit assessment, and the second part refers to the assessment of the emergent variables. So let's have a look first at the overall model fit assessment. So in general, in the SEM literature provides, we can categorize it in two broad ways. So tests for exact model fit and fit indices. So why is overall model fit assessment important? Because with the help of overall model fit assessment, we investigate whether a researcher's theory fits to the data, so to say, or whether the data is in line with the researcher's theory. So yeah, in general, overall model fit assessment is regarded as a crucial step in structural equation modeling, same as in CCA. So test for exact model fit. Originally, we proposed a bootstrap-based test, which is also known in the SEM literature as Bone-Stein bootstrap, to assess the overall model fit. And we do that in combination with various discrepancy measures. So for example, the standardized root mean squared residuals, or the geodesic distance, or the squared Euclidean distance. So these discrepancy measures, they measure the discrepancy between the sample variance covariance matrix of the observed variables and the estimated model implied variance covariance matrix. And with the help of that, we want to draw conclusions about our null hypothesis, so that the model is perfectly explains the correlational structure now of the observed variables. So here I show what actually the test for overall model fit is doing. So on the left-hand side, we have again the minimal composite model that I showed you previously. And then what the test for overall model fit does, it compares it to a saturated model, for example, to the model that you see on the on the right-hand side. And if the test rejects the null hypothesis, then our specified model shows a significant worse fit compared to a saturated model, and then we have obtained empirical evidence against our specified composite model. Next to that, fit indices were introduced in the context of SEM, because the test for overall model fit is often regarded as, or actually the null hypothesis involved in the test for overall model fit is often regarded as highly unrealistic. And this concern is mainly rooted in the work of Box, where he said, all models are wrong. So following this argument, if we have a sufficient power for the statistical test for overall model fit, all models should be rejected. And yeah, to address that issue, approximate fit indices have been proposed, and they have also been introduced in the context of CCA or composite modeling. So for example, the standardized root mean squared residual or the goodness of fit index. Both quantify the degree of misfit. The problem is, fit indices are descriptive, so we do not draw conclusions about an underlying population, and they're also non-inferential. So keep that in mind. Then we come to the assessment of the emergent variables. So this mainly refers to our estimates. And what we are doing here is we investigate whether the estimates align with our theory. So therefore, we compare our estimated parameters, the sign of our estimates, and their significance to our expectation to see whether they match. This is common practice also in structured equation modeling. And particularly important for the composite model is that we should also assess multicollinearity, or we should also assess whether multicollinearity is an issue for the estimated weights. And we can do that, for example, by considering the variance inflation factors. Yes, before I finish my presentation, I want to give special thanks to Theo Dijkstra and commemorate him. Sadly, he passed away last year, but he was very inspiring for my work. And also, as you have seen for CCA, because he was co-developer and co-author of that paper. Then, those of you who are interested in more details about CCA, so next to the publication, to my publication from 2018, I've published recently a paper together with Jörg in the Journal of Business Research, and we also published a book chapter. So those of you who are interested, please have a look at them. Then thank you.
Thank you. Applause again to you as well, Florian. Excellent.
Thanks.
We have one very short question in the chat, while already answered by Jörg Henseler. During development of a composite, is invariance test required or not? From Sandeep Singh.
Okay, so whether depends a little bit. So I don't want to equate the composite model with measurement. So therefore I do not refer to measurement invariance. But if you have, for example, a concept like socioeconomic status and you want to compare it across countries, then you should also investigate invariance. But you should not use developed approaches for establishing measurement invariance. Because here the idea is not measurement, it's rather that we form something or that we forge something. So the concept is not assumed to be measured, but it's assumed to be formed, composed, forged by its variables.
Of course. Okay, thank you. Due to time limitations, I will suggest that now we go to the discussion from Professor Henseler. Thanks again, and yes, congrats for an excellent presentation.
Thank you.
Thanks. Please, Jörg.
Okay, thank you very much, Andrei, for the invitation. And can you see my screen?
Yes.
Yes, that works. Okay. So thank you very much for the invitation. And before I go into it, I would like to make a short disclaimer. As a discussant, of course, it's one should be knowledgeable about the field, but one should also be as neutral as possible. And I guess this is quite a tricky issue in the field of composite-based SEM, because everyone has a somewhat different stance in that. So please pardon me if I'm not fully neutral. I try to be it, but it might not really work. I'll do my best. With regard to the expertise, I think that that holds. Because I just recently published a book on composite-based structural equation modeling that appeared in February, should be available everywhere. And well, some of the questions raised here could be found answered in that book. Now, I would like to look back some years. I would like to look back at the time 2013 and 2014 when PLS was under a fierce debate. There were several papers, particularly by Rönke and colleagues, by Goodhue, Antonakis, and these authors, who criticized PLS, saying that it does not do its job. It doesn't fulfill its promises, what people say what PLS would do. And in particular, they said PLS estimates are inconsistent, so they don't tell you the truth, and PLS does not have a goodness of fit test. And taking these two things together, PLS is not suitable for confirmatory research. And actually, they were right. It's exactly like this. From 2014 on, we really should know that because they're right. What to do about that? Well, in 2015, we had a PLS conference in Seville in Spain, which was a very fruitful one. And on that one, I had also the pleasure to serve as discussant of a session with 4 fellow researchers. You see them here: Win Chin, Galit Shmueli, Ed Rigdon, and Theo Dijkstra. And these researchers, they were thinking about, well, what could be the way in what PLS develops, given that what has been said to do, it doesn't do. So it must be good for something different. And what can we do with it? What can we do with the method? And interestingly, every one of these 4 had a different opinion on that. The first opinion was, well, although we know that PLS doesn't do the things that it does, we don't care. We just continue as if we hadn't heard that it's wrong. That's one possibility. We can discuss about it. A second one is, I will say, okay, PLS, as communicated before, is not good for confirmation, but it might be good for prediction. Let's have a deeper look into that. And here, particularly Galit Shmueli, who was a department head, where also Nicholas Dank worked for some time, I think. She took that position. Then a third possibility was, well, PLS does not estimate reflective measurement models, but it estimates consistently composite models. Well, if it does that consistently, so let's change the model. So if we want to estimate composite models, then PLS can do this job. So we make the model fit to what PLS does. And the fourth idea is, well, if PLS doesn't do what we want it to do, namely provide consistent estimates for reflective measurement models, we need to change the method. That was then what Theo Dijkstra and also I somewhat contributed to, that we came up with consistent PLS, which provides consistent estimates for loadings and path coefficients. Now, these 4 paths or avenues were sketched for the further development of PLS, and I'm therefore particularly happy that today in this session, 6 years later, we see that indeed these different routes are followed. And I tried to see, well, to what of these routes do these 4 papers belong, based on what I could see from the presentations given. And I had the impression that this first one, change nothing, just go on, was followed by Benjamin, in the sense that he said, well, we use PLS to estimate latent variable models, and I build on that. I built then on that another approach of measurement invariance testing of latent variables based on PLS. The second route is changing the purpose, and there then Nicholas said, okay, let's use composite models to predict individual case values. There's value in that, and let's go that route. And the third one is, well, let's change the model. Let's not talk about the latent variable model anymore. That's something where covariance-based structural equation modeling does sort of the optimal job. Well, why compete on that? Let's look for a different task, namely estimating a composite model, and there PLS might mean something for us. Although Florian also mentioned that actually there also you can use maximum likelihood. We'll come to that later. And well, the fourth idea of making PLS consistent, well, you see, I somewhat represent it, but we won't focus on this in the next minutes. I would like then to go into each of these routes a bit more deeply. First, looking at Benjamin's work, he said, well, he uses PLS to test the measurement invariance of latent variables. At least that's how I saw from the presentation, from the positioning of the paper, and I couldn't see it differently. That is, first of all, something that I really appreciate, in the sense that it is methodological research that proposes a new approach. So it's creative. It's something that for an engineer and designer, and that's what I am as part of an engineering and design faculty, is great. And say there's something that before wasn't there, and by the intervention of Benjamin, it is there, a new approach. So that is great. However, it raises some questions. The first question is about whether the tool does its job. And in that regard, Benjamin did something great, namely a Monte Carlo simulation. A Monte Carlo simulation is a great way of providing evidence, and it looked really carefully crafted, with looking at the power that this test has. And indeed, that I think is the way how research in composite-based structural equation modeling should be done. So methodologically, it looks sound. But to me, there remains the conceptual question: if PLS cannot consistently estimate reflective measurement models, that means PLS is, so to say, wrong in the case of reflective measurement model. How can you then build on that an additional approach which does something which is right? Could you explain that, how that can be possible, Benjamin?
Yes. Okay, thank you very much,
Benjamin and Jörg, maybe I just suggest to continue and for the questions for Nicolas and Florian, and then to answer jointly, maybe just to be structured and to be shorter.
Okay.
Yes.
So that that is
Thanks.
one question. Then how can that be? Because you didn't. It might be that you use consistent PLS to estimate the loadings, then it would be solved. But you don't. Then the question arises. And the second question that was also raised in the chat is about how do we cope with standardization? Because when I developed the MECOM approach, that was one of the major issues, how to deal with that, because PLS standardizes the construct scores, whereas in covariance-based structural equation modeling, you typically work with specifications where one loading is fixed to one, which means that the constructs do not, or typically not have a variance of one. So they're unstandardized. So the approach is different, and I do not see how it can immediately be transferred without some extra trick that you maybe need to tell us. Then I'd like to come to Nicholas, and I think that is the route that you're following, the prediction approach for PLS, that is certainly worth further investigation. So there is something, or there might be something to win in there. And I therefore see it with pleasure that there's a growing research group looking into that and looking into the opportunities there. Nevertheless, I was a bit doubting when I saw the title and the positioning of your presentation, where you talk about the role of prediction in composite modeling, which sounds a bit like if composite modeling is the end and prediction is the mean. And typically, one would regard it the other way around, that prediction is the end. You would like to do prediction, and composite models are a potential mean to do that. So in my eyes, I think it would make more sense to change the end and the means. And I'd like to hear your opinion about that. And another issue in your presentation, you prominently communicated that there is a move away from model fit. I know that is a point that Joe Hare brings forward, however, without any arguments, interestingly. But he repeats it very often, so more and more people begin to believe it. But I can't see any reason not to test a model, because why should one trust in a model where before one has not tested whether it is an adequate representation of the world? Just because a guru says so, that doesn't seem very scientific to me. So either the model doesn't matter, and I think in prediction, that might be a stance, that we say, well, let's do machine learning without any model inside. As long as the prediction is good, then it's fine. or we do a prediction where there is additionally insight in the mechanism. And I think that's the additional value of PLS, that you have both prediction and a understanding of the underlying mechanism. But then one would like to know, is this really the mechanism? Because making a prediction with a wrong mechanism, well, then you can do a prediction without any mechanism. Where is then the additional benefit of having a wrong mechanism? That I would like to know whether there are merits that I maybe oversee. And then coming to Florian's presentation. So it was nice to see that confirmatory composite analysis is sort of independent from the estimator. So you can use PLS, but you can also use maxVar, and you can even use maximum likelihood. And so the latter one, that's a bit triggering, namely, if you can use maximum likelihood for composite models, and you can use maximum likelihood for common factor models, where is then actually a place for PLS? Why should one use it if maximum likelihood, with its known nice properties like asymptotic efficiency and so on, if that is available, isn't then PLS superfluous? And I would also like to pick up the question that was asked in the comments. What is the difference between an emergent variable model and formative measurement, which is already known for a longer time? I think that would be worthwhile to give an explanation. So these were the points, the questions that I raised, and I'm really curious, looking forward to your answers and reactions.
Excellent. Many, many thanks. I apologize for the interruption, but as we discussed at the start, to be also on time. I will ask the speakers in the line probably of presentations to respond if you like to Jörg's excellent questions. Thanks.
Thank you.
Benjamin.
And thank you for the question, Jörg. I don't think it was that biased. I think it was very good and fair questions you put forward. Can I see the slide where you show the different proposals for moving forward? Yes. Okay. So first, for your main questions about what the underlying trick was with my simulation results. So there's no trick on these simulation results. The reason that we get nice type 1 errors and power is that I look at differences. So I look at differences in loadings. So we have an upward bias on the loadings as we expect in PLS-SEM. However, it seems that this upward bias cancels each other out when you check for measurement invariance. There's no trick. I just simulate from a common factor model and I put an intercept in, and things works out nicely. If I simulate intercept differences of 0.4, this method estimates intercept differences of 0.4. But again, it's differences. So I think that's the reason why things look good on these simulations. Okay, and then for the other thing here, so I would just, you have these 4 different routes of going forward. So I would actually add a 5th to this one. So the fact that PLS is biased and only consistent at large. So for the people who don't know that, we need both the sample size and the number of indicators in each construct to go to infinity at a specific rate before we don't have any bias, or before we have consistent estimates. I think the best way to go forward with PLS is to clearly acknowledge that we have a biased estimate. So we have downward bias in the inner path estimates. We have upward bias in the outer loadings. But then say, okay, there's no specific estimation method that is either totally wrong or totally the best one. So what kind of circumstances is PLS suitable? So if we ask the question, is the path coefficient 0.001 0.25 or is it 0.35? This is of substantial importance to us if we have either or one of these path coefficients. Then you should not use peerless. That is what my take on it is. However, if you ask, do we have a significant relation, and is another relation, is that higher in the path coefficient than another relation? Well, then you can use peerless. Also ask the question, which estimation method is most robust to misspecification? So if we have that, we have actually specified the population model, which is highly unlikely, well, then we should use C-SEM. I would say that because then you get the correct estimates. The problem is that we don't know that. So we need to understand what kind of differences there is in robustness between, for example, peerless and C-SEM. The last thing is we also have the possibilities to use latent variable scores in peerless. And the working paper I just presented showed one way to use these latent variable scores as, I think it was Wold who said it, conveyors of the information. So I simply compute these and I use them in a total different setting, and the estimates still make sense. I think that's a strong thing for PLS also. So I think that prediction, that is definitely interesting. Change the model, composite. Well, then we change the underlying population model. We need to justify that model. We need to say which kind of circumstances is this one appropriate in. And there is, of course, circumstances where we have such a population model. And in those cases, PLS does a superb job at estimating the coefficients. There's other circumstances. Schubert, Florian, you listed some of the cases. Well, then you know that if you are in one of those cases where you don't have a composite, well, then you should take into considerations that we have the PLS bias and the different things that we have there. Okay. I think, okay, one last point. I know I should make it short. Bias in itself does not need necessarily to be a problem. Also think about principal component analysis, widely used, biased also for the loadings, but it's used as an approximation, which is well understood that it's only approximation. So I don't think this should be the only benchmark to just tell us which kind of estimation method we are using. Okay, so that was what I had.
Thanks a lot. Great responses. Please also Nicholas now. Nicholas, thanks.
Thanks, Jörg, for those tough questions. It's a bit hard in this format to remember the questions from like 15 minutes ago, so I'm going to give it a bash. Please excuse me if I miss just a little bit. I tried to write it down as fast as I could. So the first question related to the ends versus the means, and you indicated that perhaps prediction was the end. If prediction was the end, there are dramatically superior algorithms, and not necessarily just like machine learning or black box methods, but even fairly interpretable explanatory models. So prediction most certainly is not the end. I would argue that it's the means. Just like inferential statistics are the means to draw conclusions about our hypothesis, the predictions are also a means to gain additional evidence as towards the generalizability and the value, the practical value of the model. So I still believe it is the role of prediction in composite modeling. So a second question, and I wrote it down terribly here, is the point about model fit. So actually, I agree with you. Well, I think I do. Let me say that. So my point is not that you should not rely upon model fit, but that you should not rely only upon model fit as the singular measure. So I advise complementary analysis rather than substitutive analysis. And as to the third question, it was something regarding the mechanism and the model being possibly the wrong model. And I forget actually, but what I wrote down here was the box comment that I think Florian included in his presentation, that all models are likely wrong, but they're wrong but useful approximations, and again reinforces this need to quantify the utility of the model, which I think predictive evaluation does a good job of. Yeah, so thanks again, Jörg. Those were tough questions, got my brain thinking, and I really appreciate being here tonight.
Okay, thank you, Nicholas, and also I give the word to Florian.
Yes, so thanks, Jörg, for your questions. Yeah, so one was that now there's this maximum likelihood, or that specification that allows to estimate the composite model by maximum likelihood, and why is there still a need for PLS? So yeah, my argument is, I mean, having several estimators is always a good, yeah, it's always good to have several estimators, particularly if we look at the recent developments in structural equation modeling, where people actually try to or step back from estimating the complete model at once, so simultaneously, and yeah, try to split the models. So they use more limited information estimators over full information estimators. And I mean, following this argumentation, I would say it also applies to the discussion about maximum likelihoods versus partial least squares, because yeah, PLS is a limited information estimator, I would say. So therefore, I mean, yeah, so far it has not been shown that PLS is always superior to maximum likelihood. So I mean, one need to investigate it in more detail. What about model misspecifications? What is the behavior of the two estimators in the context of composite models? And yeah, so we need to shed more light on that. But yeah, so far I would not cancel or say, yeah, don't use PLS for composite models, as long as we don't know whether PLS is always worse than maximum likelihood. And then with regard to the formative measurement, so what is the difference between the composite model that I showed you and the formative measurement model? So typically in the formative measurement model, we assume that the concept, so from our theory, is represented by a latent variable as well. So similar to the reflective measurement model. So we assume that the causes, so we assume that the causes we assume that the observed variables are causes of the concept. So and then it's modeled as antecedents of a latent variable. In contrast, in the composite model, we do not model the concept as a latent variable, but as an emergent variable, so as a composite of its ingredients. And I would argue it, yeah, it is also more, yeah, we actually need to go one layer higher, so in the theory level, so where we say, if we want to measure something, right, then we need to assume that it exists. So, and then if we think a concept exists, then we can measure it. But the composite model, as shown here, it's used to model concepts that are formed, so they are not existent per se. So that's I would say is the difference between the causal formative measurement model, how it's called in the context of C-SEM, and the composite model, as I've shown here. Yes, so these were my answers. I hope they are sufficient.
Okay, thanks. Maybe Jörg, if you want to add something additional to the responses. Thanks.
I'm with the answers. Thank you very much for the answers.
Great, thank you. And now I would open the floor to questions. Naturally, applause again to all the presenters and for the excellent discussion. Basically, if anybody has any question, please put on the chat, or now you can also unmute. I hope this would be possible. I will start with one that was still in the chat during the discussion and the presentations. It was shortly answered, I think, by Florian. What do you mean with consistent PLS? How is consistency included in the PLS estimation? I think this was.
So who shall answer? Because I mean, this issue was raised by Jörg, right? So Andre, okay? Then I will answer. So the problem is that PLS creates a linear combination of the observed variables that are assumed to measure a latent variable. So one share of the variance in an observed variable is assumed to be caused by the latent variable, and another part of the variance, as we have also seen on the slides of Nicholas, is caused by random measurement error. And so if we build a linear combination, also this linear combination contains measurement error. And then if we use this linear combination to estimate coefficients, the estimates are biased due to attenuation bias. So to overcome that, consistent PLS was introduced, which corrects for this attenuation effect, so to say. So it corrects by the reliability of the PLS scores. And then, yeah, as it was shown, you can obtain consistent estimates for common factor models.
May I add a point here? Because I think this question is triggered by, well, given the dominant views on PLS, what is currently stated, what reflective measurement model is, why do we then need consistent PLS? Well, the reason is there are some people in the PLS literature, or some proponents of PLS, who say that PLS estimates reflective measurement models. For instance, when you read the textbook by Hare and colleagues, then they state PLS estimates a reflective measurement model. But it's wrong. PLS doesn't do that. PLS estimates a composite model. So if you really want to know the consistent coefficients of a reflective measurement model, you need to have this modification that Florian explained. So PLS does not estimate reflective measurement models per se, and those who claim it actually lie. They redefine it. So you must check in the book by Hare, they define reflective measurement differently to the whole psychometric literature. And I think this is an issue of scientific integrity, actually. Because that leads to that some people ask, well, why do we need that for reflective measurement? Yeah, it is because they give a wrong representation of reflective measurement.
Thanks. Anybody else? There seems another question. From Diogenes Bible, questions about formative measurement. There is a reference and two questions. Changing endogenous variables, it changes weights of the exogenous composite. How about the meaning of the composite? Changes from one research to the next.
Yes, so I guess it refers to me, right? Because I talked about the composite model. So yes, indeed, the composites are context specific, but I would argue also the forged concept is context specific, because usually a concept is formed or created or designed with a certain, for a certain purpose, so to say. So also from a theoretical point of view, the form concept, changes with or at least its purpose changes with the context. So therefore I see no real big issue that also the composite model, I mean the statistical representation, changes if we change the model, because then we investigate a different theory. How about the meaning of the composite? I mean, the meaning, so we have the weights, And the weights described, how is the composite defined? So how is the emergent variable defined? It's a kind of recipe to build the form concept. So I'm not sure whether this is meant by with the meaning of the composite. Perhaps Diogenes
I try to explain. If we change the weights, I think kind of a recipe when I cook a kind of a pizza or something like that. Yeah. If you change the quantities of the ingredients, we do not have pizza. We have another kind of bread or stuff like that. And for this reason, I say meaning.
Yeah, but perhaps then in your context, pizza is something to make someone, what is it, not hungry anymore, right? But I mean, then if you, for example, want to create a pizza that makes someone work faster, then you need to change the ingredients. Perhaps then labeling it as a pizza is not the right thing anymore. But yeah, it can still be consist of the same ingredients. But then they are differently weighted. So for example, use more salt. I don't know, I mean, it's just coming up to my mind. So likely ridiculous example, but yeah, use more salt, then people work faster.
Maybe I can add here also that you must say Wilcox, Howell and Breivik, they come from an empirical realist stance, and they believe in the true concept. There is that one true concept that you would like to measure. Yes. However, composites are about, as Florian said, about designs, about constructions. So think, for instance, about cars, artifacts that everyone is familiar with, and then the concept underlying a car could be carhood. Now, is there the one true carhood, or can you have some variation in there? For instance, if you want to transport luggage, then your carhood or your optimal carhood is somewhat different as if you want to impress, let's say, some ladies at the cafeteria that you drive by. And then maybe not a large space for cargo, but maybe then a car with an open roof would be more appropriate. But still, both of these artifacts have carhood, and it's not that the one has true carhood and the other one has wrong carhood, but we allow different recipes, a different weighing of the ability to convey cargo or the ability to impress others. We allow for that. And it's not a problem when it's about forged concepts, because you have these different purposes, as Florian says. Once you want to impress others, you want to make your neighbor envious with your car, and others just want to transport people from A to B. So that is fine. It's not a problem. It's only a problem when you think of the one true carhood and everything else is wrong. Then it's a problem. But if you step away from that, then having different weights, different recipes, is a nice reflection of what actually happens in the world.
Like, just one a little question. I think about the longitudinal comparison with this kind of a composite, because if the weights change, I talk about the semi index. This is the issue.
Florian, sir?
Sorry?
Yeah, hello, I'm Dr. Sandeep from India. My question is about, there is an article of Hare et al. About the measurement of the composites. In this article, they are discussed about the measurements of the things that are the composites. So your opinion about the composites and that articles has, I think, the different concepts. So would you like to comment on it?
So it refers to me, Sandeep, the question? I guess, yes, right? Yeah, I mean, yeah, so I elaborated already a lot in my recent article that I also showed on the first slide. So where I think they are not, correct, or that it's not a good idea to use yeah, where I raise my doubts, let's call it in a more neutral way, about the usefulness of using metrics that have been developed for reflective measurement models. I don't know, like average variance, extracted, all these things, and base them on parameters estimated by PLS. So I'm not sure whether this is a good, so yeah, I mean, I'm sure, but I would not recommend because it's not a good practice. So yeah, so why they are doing that, I guess it's better to ask them.
So actually it's quite confusing to following the two views because they are similarly using this word composites, and
Yeah, I
similarly
agree.
it is quite confusing for all of us, being when we are going through the literature, those who are on the learning stage, that will got a big confusion what composite they will use, whether they will use that as a measurement or whether they will use the artifact or the forged conceptual.
Yeah, I think the confusion is also rooted in the fact that Jörg described, so that they label reflective measurement with mode A and formative measurement with PLS mode B. So, and actually the two modes are just different ways to determine the weights. So in the end, you still have a composite. So it's not the reflective measurement model or the formative measurement model as known from the SEM literature. It's just something from the PLS-SEM that evolved in the PLS-SEM literature. So yeah, I would not regard my approach as an approach of PLS-SEM. So as I also mentioned on my second slide, so yeah, where I raised caution about this mislabeling. So now we have two methods, CCA, one in the context of PLS-SEM and one which was actually developed as an approach to SEM, so to covariance-based SEM, if you want to label it as this. So yeah, I can fully understand that now there's confusion.
Can I add a comment?
Yeah, sure.
Okay, so I can also understand there can be some confusion here. So my view on this is that you have the population assumption. How does the population model looks like? Then you can assume a composite. In my opinion, we need to better define across the different streams of the literature how we define a composite population model. So we can have different kind of definition of that. Then on the other hand, then we have how to estimate a model. Nobody says that PLS or any other method. You can choose any method you want to estimate any of the population models. Some estimation methods are better suited at some specific population model. But we should keep those two things apart. There's estimation and there's population model. That was just my clarification about that. And when you choose you should not choose the estimation method first and then define the population model. So define the population model first and then choose your estimation method. And then you should be well informed of the benefits and the downside of that model you use. That was just my point on that.
May I add here, Benjamin? I'm fully with you. I think that's the great suggestion. They say, well, first comes your view of the world. How do you understand the world? That in your mind as a researcher, do you think there is something built or created? Then it could think of a theory that contains that. Or do we have there a concept which exists and we might have reflections of that somewhere in the observed world? So first comes our theory, and then you must find then a method that can specify a model according to that theory and then estimate it. So that should be the order, not only because I manage PLS and I don't know any other method that I then must choose the model that comes best with it. So indeed, first should come the theory, and then you raise that point and say, well, for the reflective measurement, we have the measurement theory, and that is well established, and that is, we know what we have. Whereas on the other side, for the composite model, we have not yet that fierce understanding of this population model. What exactly is that model? How does it look like? How should it be parameterized? And that is indeed very fresh knowledge, and we are working on that but we have published an auxiliary theory, which is the synthesis theory. It's also part of that book that I mentioned, which is a sort of analogy to measurement theory. So synthesis theory, a theory of building an artifact that emerges, would then be that theory that you are looking for. They say, well, why would there be this population model? Why it would be if something is in line with that theory.
Thanks. Basically, I will propose that we end at this point. If you agree, there were a lot of discussion also in the chat throughout. I will just point to one additional issue already answered in the chat, was about software. I will not continue because I saw there are multiple software packages, and I will rather not ask. It is also partly in the chat. So thank you to all. The session, as was asked already in the chat, was recorded. It will be accessible in few days on the Young Stats YouTube channel. Again, thanks to all, in particular, again, to Florian for his initiative and great help, for the excellent discussion that was provided, and to all the speakers and naturally also the participants for your questions. We continue in 1 month with the webinar on functional data analysis, again, with excellent young speakers. You can check this already on Young Stats website. So again, thank you to all, and hoping you follow both Composite-SEM and the activities of Young Stats also in future. Thanks. Thanks to all.
Yeah, thanks, Andre.
Bye.
Thank you very much.
Bye-bye.
Bye.
Yeah.
Thanks.
Bye.
Thank
Bye.
you.
Bye.